All right, welcome everybody. So in this video, I want to take a look at some more examples of subsets of vector spaces and checking to see whether those subsets satisfy the three conditions required to be a subspace. So the three conditions again are, does that subset contain the zero vector? Is that subset closed under vector addition? And is that subset closed under multiplication by a scalar? So the example I want to take a look at first is we're going to let our vector space be R4, and we're going to use the usual operations, vector addition and scalar multiplication. And I want to consider subspace H, which consists of vectors in R4 that are of this form. So the first entry can be written as 2 times some number A plus 3B. The second entry is negative some real number D. The third entry is 0. And then the fourth entry is 6 times some number C plus 2 times the same number A that we had in the first entry minus the same number B that we had in the first entry. So we want to check to see whether these properties are satisfied, these three properties. So is the zero vector in H? Yes, we just set A, B, C, and D all equal to 0. And that's going to give us 0, 0, 0, 0. So the zero vector is in our subset H. Property 1 is satisfied. Let's check what happens when I add two vectors. So I'm going to let my first arbitrary vector I'm going to denote it with subscripts 1. So this would look like 2a1 plus 3b1 minus d1 as the second entry. 0 needs to be the third entry. And then the final entry is 6c1 plus 2a1 minus b1. And then our other vector has a similar form, but we might have different numbers. So it's going to have 2a2 plus 3b2. We have a minus d2 in the second entry. The third entry needs to be 0. And then we have a fourth entry where we have 6c2 plus 2a2 minus b2. And then we add these two vectors together using our typical vector addition. And then I'm going to group things together. So I would have my a1 plus a2. They're both being multiplied by 2. I've got my b1 and my b2, which are both being multiplied by 3. So I can write this as 2 times some number, which happens to be a1 plus a2, plus 3 times some other real number, which in this case is b1 plus b2. And we can do the same with the other entries, and you can verify that what I get is a vector which can be written in the form of our general vectors in subset H. So we can see that if I take any two vectors in H and add them together, the resulting vector is going to be inside of H as well. So that means this is closed under vector addition. And then the last condition that we need to check is this closed under scalar multiplication? And that is a little less tricky to verify. If I take some scalar k times an arbitrary vector in H, we get something back that looks like an arbitrary vector in H. So this kind of strange looking subset of vectors actually does form a nice subspace in R4. Okay, so let's check another example where we're going to think of our vector space V again as vectors. So here we're going to think of V as R3, and we're going to have the usual operations of vector addition and multiplication by a scalar. And the subset that we're going to consider now, H, is going to have first coordinate 3a plus b, where a and b are denoting any real numbers. The second component is going to be a plus 5, and the third one is 2a minus 5b. So we want to check to see whether we have the zero vector in here, whether this is closed under vector addition and closed by scalar multiplication. So let's check the first condition, is the zero vector in here? And if we have the zero vector inside of H, the first thing that I can see is, well, a would have to be minus 5 because I want this second component to be 0. So if we set a equals minus 5, then looking at the first component, we would see that B would have to equal 15. So if I set A is equal to -5 and B is equal to 15, we have a first coordinate, which is 0. Our second coordinate is 0, but plugging these values in for the third coordinate gives us -10, -75. My arithmetic here should tell us that this is not -65, that is -85, which is not equal to 0. So if I pick values for A and B that make the first two coordinates 0, I'm going to get a non-zero entry in the third coordinate. And similarly, if I tried to pick value after I pick A is equal to -5, I pick a value for B that's going to make the third coordinate equal to 0. That's going to now make the very first one non-zero. So the vector 0, 0, 0 is actually not inside of this subset H, and that rules out the possibility that H could be a subspace right away. There is the 0 vector does not live inside of H. But just to kind of see some practice with these other conditions, they also fail. So if I were to take, here I picked a specific example. So let's say I take as my first vector, A is equal to 3 and B is equal to 0. So then that vector would look like 3 times A plus B, 3 plus 5, 2 times 3 minus 5 times 0. And then for my second vector in H, I picked the vector where A is equal to 0 and B is 1. So that would give us a vector of 0 plus 1 in the first entry, 0 plus 5 in the second entry, and 0 minus 5 times 1 as the third entry. And now if I add these two vectors together using our standard vector addition, I would get 3 times 3 plus 1, 3 plus 5 plus 5. So I get a plus 10 over here. Then I get a 2 times 3 minus 5 times 1. So it almost has the same form as H, but I've got a 10 here instead of the 5. So this is actually not in H. And you might be thinking to yourself, is there some other way, although A was 3 here and B was 1 over here, maybe we can pick different values for A and B to express this vector in a form like this, but you'll kind of hit a dead end, similar to the way that we hit a dead end in question 1. So what's causing the issue here is when we add these two 5s together, we get a 10, and we don't get the plus 5 that we're looking for in the second position. And similarly, if we want to check whether this is closed under multiplication by a scalar, then this needs to work that for any scalar k that I multiply this vector by, I should wind up with something in H. So let me pick k to be the scalar 0. If I multiply 0 times any vector H in that subset, we get the 0 vector back. And we already verified way back in number 1 that the 0 vector is not inside of subset H. So here what you can see is if I want to show that these properties do not hold, like closed under addition or closed under multiplication by a scalar, then I just need to pick one such counterexample, because this needs to be true for all vectors in H and all possible scalars. So if I can show that there exists just one scalar, such as k equals 0, that violates this property, then that's enough. And so we certainly have shown that here. So this subset H inside of R3, although R3 is a vector space and it has its nice normal usual operations, picking any subset is not going to guarantee that we get a subspace. So this subset does not satisfy any of the conditions for being a subspace.